Okay, there's a couple of things we can talk about integrals. One is the mean value theorem for integrals. And basically, here's what it says. It says if f is continuous on a closed interval, then there exists a number c in the closed interval such that the integral of f of x dx is equal to f of c times b minus a. Another way this can be rewritten is to say that there's some number c, f of c, that is equal to the integral divided by the length of the interval. But when you take an integral and divide by the length of an interval, you actually get what's called the average value of that integral. And so this theorem actually directly leads to the average value theorem that we'll get to in a minute. But anyway, let me just show you an example that you might deal with from here. So suppose you're given a function 3x squared, and you're given the interval from 1 to 3, and it says find c that satisfies this mean value theorem. Well, the first thing I want to do is I want to find what this integral would be from 1 to 3. So I'm going to evaluate the integral 3x squared dx from 1 to 3. Well, I intentionally gave you an easy one here. This is just integral of x cubed from 1 to 3. And if you integrate that from 1 to 3 using the fundamental theorem of calculus, that's going to be 3 cubed minus 1 cubed, which is 27 minus 1, or 26. So that's the value of the integral. Now, we need to find c. To find c, we must set the integral equal to this, f of c times b minus a. Now, we don't know c, but we do know what b minus a is. We do know that b is 3 and a is 1. So we've got to find c such that f of c times 3 minus 1 equals 26. In other words, 2 times f of c has to equal 26. So solving that for f of c must equal 13. Okay, but what is f of c? Well, the function was 3x squared. So f of c would be 3c squared. So 3c squared has to equal 13. And so now we just solve the equation for c. So c squared would equal 13. 3c squared equals 13. Then c squared would equal 13 over 3. And c would equal the square root of 13 over 3, which is 2.1. Now, I didn't use the negative square root simply because I knew that the interval is positive, so it's got to be a number in that interval. So c is the actual number. Square root of 13 over 3 is the number that actually satisfies the mean value theorem for that function on that interval. So as I said a minute ago, when you take the integral and divide it by the length of an interval, then you get what's called the average value of the function. So actually, if you want the average value of this function over this interval, well, we already have it, because the integral up there we knew was 26, and then if you divide that by the length of the interval, well, you're just basically dividing 26 by 2, so the average value of that function is 13. Okay. Now, there is a second fundamental theorem of calculus, and I don't spend a lot of time on it in business calculus. In a Calculus 1 class, you might spend some time on it. But basically, it says if f is continuous on an open interval I containing a, then for every x in the interval, if you take the derivative of the integral from a to x of f of t dt, you're going to get f of x. Okay, so this is basically the inverse property of differentiation and integrals at work. We just have to use different variables in this theorem. Okay, so let's take a look at something here. Let's suppose that f of t is 2t. All right, now what would happen if you evaluated this integral? What would happen if you evaluated this integral? In other words, what would happen if you evaluated the integral from a to x 2t dt? Well, you would actually get t squared from a to x, which would actually equal x squared minus a squared. That's what that's supposed to say. So you'd have x squared minus a squared, where a is a constant. Well, if you took the derivative of this, now the theorem is saying I don't have to show any work, that I know that the derivative of this is simply going to be this function evaluated at x. So the answer should be just 2x. All right, but let's say that you didn't trust it. So we would have to take the derivative of this integral. Well, up here we figured out what this integral is. It's x squared minus a squared, where a is a constant. Well, you know the derivative of x squared minus a squared is just 2x. So you can see that you just get the same function evaluated at x. Okay, so basically, let me just show you one more time. If you had the derivative, if someone said, what's the derivative of this integral from, say, just pick a number. How about 3? From 3 to x. Okay, what's the integral from 3 to x of, let's, pick some function. How about 1 over x dx? How about that? 1 over x dx. All right. Then basically, up here, actually, I put dx. I should have put t. 1 over t dt. I know it's confusing. You're supposed to use a different variable. All right. So now, it actually is going to be the same function that's in here, but evaluated at x. So it's actually just going to be 1 over x. And that's all there is to it. And so basically you're saying that if you take the derivative of the integral of some function, you're basically just going to get right back to that function that you had in the integral. Okay, so basically here, if you integrate from negative 2 to x, t squared minus 1 dt, and then take the derivative, you're just going to get x squared minus 1. And then the same thing here for square root of t dt. And then if you take the derivative of the integral 0 to x square root of t dt, you just get square root of x. Now I'm going to finish this. I've got one more application, I believe. This is kind of a strange character, but it's a net change theorem. It basically says the fundamental theorem of calculus states that if f is continuous on the closed interval a to b, and capital F is an antiderivative of little f on a to b, then this is true. Well, we already knew that. Okay, but we could also write that the integral of f prime of x dx, if we integrate f prime of x dx, that equals f of b minus f of a, where f of b minus f of a represents the net change in capital F on a to b. So net change of the capital F over the integral from a to b could be written like this. All right. So let's just take a look at this problem, and if you don't completely follow it, it's okay, because it's probably not something your teacher's going to ask you to do anyway. All right. A chemical flows into a tank at a rate of 200 plus 6t liters per minute. T is a variable, where t is from 0 to 75 minutes. Find the amount of chemical that flows in the first half hour, the second half hour, or the first hour. Well, since this represents the rate of flow, that's not the actual flow function, that's the rate of flow. So that's actually the derivative of f. F is actually the flow. So basically, that's f prime. Well, if you integrate that function from 0 to 30, that's for 30 minutes, 0 minutes to 30 minutes, and then evaluate it, you'll get 8,700. I'm not going to go through the evaluation because you know how to do this by now. So if you evaluate this using the fundamental theorem of calculus from 0 to 30, you get 8,700. Well, then if you evaluate it for the second half hour, you would evaluate the same function from 30 minutes to 60 minutes, and you would get 14,100. So in other words, during the first half hour, the net change was 8,700 liters. During the second half hour, the net change was 14,100 liters. Now, to find the net change over the entire hour, I don't really have to do the integral like I did here. I'm integrating from 0 to 60 because I already have the net change for the first half hour, the net change for the second half hour. So the net change over the entire hour, you would just add these together and you could get 22,800 liters. All right, but if you do it this way, it works as well. You'll get the 22,800 as well this way. So anyway, that's pretty much ends this section on the fundamental theorem of calculus, and now we're going to talk about a little about area.